Welcome to Lab 4, the Spectrometer lab. In this lab, you will learn some basic concepts in optics and photonics. You will also use a simple spectrometer setup to characterize a dye called erythrocin extra bluish. Let's begin with the pre-lab, building a fiber-coupled LED light. The components of the pre-lab include a super bright white light LED, a 200 ohm resistor, a battery strap and a 9-volt battery, a piece of multi-mode fiber, some sandpaper, epoxy or glue, and a stick for application. You will need to sand away the plastic in the front of the LED to make better coupling with the fiber. Start with a rough sandpaper and use the finer sandpaper later. You may sand close to the bond wire, but make sure not to break it. In the first part of the lab, you will be observing the Fresnel coefficients. You will measure Fresnel reflections from a semicircular acrylic prism. Here's the setup as viewed from the top. You will use a red diode laser, a linear polarizer, the acrylic prism mounted on a rotational stage, and a high sensitivity power meter. Begin by characterizing the polarizer. You can understand the direction of the polarizer by looking at how it attenuates light reflected from a flat surface. Set the polarizer to pass the TM polarization. Align the back reflected beam toward the incoming direction. This will calibrate 0 degrees or normal incidence. Now measure the incident power. Change the angle of incidence by rotating the stage and measure the reflected power. Note the critical angle at which the transmitted power goes to zero. For the TM polarization, there is also a Brewster's angle at which the reflected power goes to zero. Now use the TE polarization and make the same set of measurements. Now you will observe the index contrast in the fiber. Using the LED-coupled fiber you made in the pre-lab, the numerical aperture is easily found by observing the angle of the output light that's projected on a protractor. The refractive index of the fiber core is given in the handout. The numerical aperture formula allows you to easily calculate the refractive index contrast. In the next section of the lab, you will be working with a liquid core waveguide filled with ethylene glycol. Make sure you're wearing gloves for this part of the experiment. Start with a length of Teflon tubing of about 100 millimeters length. Extract some of the ethylene glycol using a clean syringe. Use the syringe to carefully fill the Teflon tubing, making sure there are no bubbles. It's ideal to have a small droplet at the end of the tubing. Now carefully place the waveguide flush against a piece of glass glued to a fiber V-groove holder. This effectively seals the end of the waveguide. Couple the LED-coupled fiber into the end of the waveguide by inserting it into the Teflon tube. Measure again the numerical aperture by observing the divergence angle using a protractor. Because the index of the Teflon tubing is known, this will allow you to calculate the index of ethylene glycol. The final in-lab component is an experiment using a home-built spectrometer setup. Construct the spectrometer setup according to the drawing in the lab handout. The light source will be the fiber-coupled liquid core waveguide you just made. Set up a black screen with an X to focus the camera, a digital camera, a thin transmitting grating, a flat mounting plate, and 4 vials of erythrocin extra bluish at different concentrations. Note that vial 4 is just water and used for calibration. Once the focus of the camera and position of all components are optimized, fix them to the table and do not move them for the rest of the experiment. The camera should see a spectrum at the image plane of the black screen. First, remove the LED coupled fiber and insert instead a plain piece of fiber into the waveguide. Calibrate the spectrometer by taking data for a green laser at 532 nanometers and a red laser at around 650 nanometers. Replace the LED coupled fiber once you're finished with the calibration. Mount each dye concentration in front of the light source and take the spectrum. Make sure to position the cuvette so the propagation thickness is 1 centimeter long. You will calculate the absorption and molar extinction coefficients in the post-lab analysis.